Going live. Yeah, I think there's a little delay. Okay, perfect. Welcome, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'll be your host today. Today, we're presenting on the stability of Kerr black holes by Rita Teixeira da Costa. She got her bachelor at the Instituto Superior Técnico in Portugal, and then she moved to Cambridge, where she did her master's and PhD, and she got recently her PhD at the University of Cambridge under the supervision of Michalis Daferos. She's now an NSF postdoctoral fellow at Princeton and a junior research fellow at Trinity College in Cambridge. Rita's research focuses on differential equations arising with connection with general relativity, and her works really represents an important rigorous mathematical progress on several open questions related to black hole stability. She recently won the dissertation prize given by the Association for Women in Mathematics. And according to one of the experts' letter, this is something I was stalking Rita, says that her thesis is an outstanding piece of work that resolves a major problem in the field of general relativity. It is a pleasure to have Rita today. Remember that you can ask questions over email, through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. So now, without further ado, we'll turn in time over to Rita. So thanks for joining us, and Rita, the floor is yours.
Thank you so much. And it's a bit embarrassing that you talked me up so much, because now I feel the expectation is very high. But thank you. It's really a pleasure to be part of this. And it's great to have met all of the organizers, and hopefully to talk virtually with other people in Latin America who are interested in this. So I want to talk about the stability of Kerr black holes, and I know that not everyone in the audience will be coming from a mathematics background. So I want to start with a kind of more gentle introduction, and then at the end things will get a little more serious. And this is basically what Alejandro said: I should start gently, but at the end everyone should be dying for me to shut up. So let's start with the gentle introduction. So as I said, as I said, I'm going to talk about the black hole stability problem, and this is a 65-year-old problem. And I want to start by convincing you that this is still an open problem. So a disclaimer here, because this audience is, I know, composed of people who come from many different backgrounds in physics and probably mathematics as well. This talk is really about general relativity, and in particular, it's about the vacuum Einstein equation. So Ricci tensor of G is equal to 0, where G is the Lorentzian metric on a Lorentzian manifold of 4 dimensions, so space-time. Okay, and this is all that I'll do. So very classical general relativity. And the black hole stability problem, as far as I know, really goes back to this work of Reggie and Wheeler in the 50s. What they do in this paper is that they note that the Schwarzschild solution is a stationary black hole, and so it is in some sense an equilibrium state for the Einstein equations. And so they ask, well, if this is an equilibrium state, is it a stable equilibrium or an unstable equilibrium? Okay, and I've written here the Schwarzschild metric. Okay, at this point, as you can see, obviously from the title and the abstract, people were still not completely sure what the Schwarzschild solution meant. And a few years later, it became clear that this question that they were trying to answer, the question of stability for Schwarzschild, was false. And it was false for trivial reasons. It's because when you perturb a Schwarzschild black hole, you will generically end up with a little angular momentum. And so you'll end up with a Kerr black hole, which at the time weren't known yet. So really, the Schwarzschild solution, the exterior, the black hole exterior, this can only be stable within the larger class of Kerr black holes. Okay. And this, as you probably all know, this is a more general stationary solution to the Einstein vacuum equations. This is the metric. It's a little more ugly. And this is now not spherically symmetric. It's axisymmetric, and we still have a mass here, a mass m, but now we have a parameter a, which represents the rotation of the black hole. And I'll use this notation. I'll say that if it's smaller than m, then we have a subextremal black hole. If it's equal to m, we have an extremal black hole. The case where you don't satisfy the inequality a smaller or equal to m is not a case where you have a black hole. Okay. And I just want to point out here that this stability within the larger class of black holes, this actually can be made precise. So this has been done in recent work of the firm of Solzhenitsyn, Rodniatsky, and Taylor from 2021. And they give a very precise meaning to the statement stability of Schwarzschild within the larger class of Kerr black holes, and they give a full rigorous proof of this result. Okay, and there's also earlier work of Kleinerman-Sheftel, which also proves this statement, but for perturbations which lie in a symmetry class. That is not the case in this other work. This is without assumptions of symmetry. Okay, so really, these works on Schwarzschild, the formalism for investigating the question of stability in the 60s, it was really gearing up, I suppose. So there was, after Reggie and Wheeler, there were works by Bardeen Press, someone whose name starts with V, which I can never pronounce, Vishevara, and other people who were writing down many equations which were relevant for the investigation of stability of Kerr. But all of these equations were very much tied to the spherically symmetric aspect of Schwarzschild. And so it wasn't clear exactly how to adapt this formalism to understand Kerr black holes. And really a big breakthrough in understanding the stability of Kerr black holes, of rotating black holes, came from Teukolsky only in the 70s. So Teukolsky took the Newman Penrose formalism, which was developed in the 60s for understanding perturbations of the Einstein equations, really. And he understood something very spectacular. He understood that if you look at the Newman Penrose formalism and you focus on the so-called extreme curvature components, then they satisfy an equation which completely decouples from the rest of the system of linearized Einstein equations. Okay, so if you look at linearized gravity in this Newman Penrose formalism, you will find that you have a million equations, but there's two particular components which satisfy equations which decouple from the rest of the system. Okay, and those two particular components happen to be gauge invariant components at the linear level. And so if you want to understand the stability of Kerr, you have to start by understanding the linear stability of Kerr. So the Einstein equations are nonlinear, so you first have to understand what happens when you do linearized gravity, when you assume that perturbations of Kerr are so small that the quadratic terms don't matter, just the linear terms matter. And it turns out, something completely non-obvious, that when you write these linearized Einstein equations, suddenly you have a huge system, but there's two special ones which decouple from the rest, are completely independent. And the variables that these equations relate to are variables which are gauge invariant, so extremely physically relevant. Okay, and this is true in the case of gravitational perturbations, but it's also true in the case of electromagnetic perturbations and others. And this is why this equation came to be known as the Teukolsky master equation. There's a way of putting together writing in a single equation by introducing this parameter S. There's a way of writing in a single equation the equations for many types of perturbations of black holes, again at the linear level. Okay, so after doing this, Teukolsky, I think with his PhD advisor, I think Press was his PhD advisor, they then looked at separable solutions of this equation, of this master equation. And I should point out that the existence of these separable solutions is not obvious. It's something which follows from very non-trivial work of Carter in the 60s, who found that Kerr had this additional conserved quantity which allowed the wave equation to be separated. Okay, but anyway, so they knew by then that you could have separable solutions to this Teukolsky equation, and so they looked at solutions of this form and looked at possible unstable modes. So unstable modes, now what I mean by this is just modes which have positive imaginary part of omega. So if you take positive imaginary part of omega here, you'll see that this is a solution which is exponentially growing in time. So you have here an instability. Okay, you want to, maybe I should have pointed this out before, but if you look at Kerr, the exact Kerr solution, this alpha, this extreme curvature component that I mentioned, it will be 0. And so you want to be as close, if you want stability of Kerr to hold, you want to be as close to 0 as you can. You don't want to be exponentially growing in time. So they looked at this kind of separable solution and they tried to rule out the existence of unstable modes. Okay. And why can you expect that there might be unstable modes? Well, in principle, these are possible because on Kerr, there is this funny feature which is called superradiance, or sometimes, and you know, sometimes this is referred to as the Penrose process. So in Kerr, you have this region of spacetime, which is the ergo region, where the vector field, which is stationary, ceases to be time-like, okay, and starts becoming space-like, okay? So what happens is just that the direction of time is somehow not aligned with the direction of the stationary of the stationary killing field, which is kind of funny. And it leads to this Penrose process, which is a process, it's a theoretical experiment where you send in a particle to a Kerr black hole. And once it's in the ergo region, it divides into two. And you by this process, because of the energy being measured with respect to the stationary killing field, which now is space-like, you can have the one of the particles come back to infinity with more energy than the particle which you shoot it in had. Okay, so that's a Penrose process, and the similar thing is possible for waves. This is called superradiance. So if you have this condition that omega times omega minus this factor, which depends only on the azimuthal number of your separable solution, little m, and on the Kerr black hole parameters, if you have this inequality, then you cease to have control over the energy of your waves. Their energy might grow, similar to the Penrose process, where the energy of the particle that comes out is larger than the energy of the particle that goes in. Okay, and actually these superradiance instabilities, they are present, for instance, in massive Kleingordon. This was already conjectured by Princeton and Teukolsky in their famous black hole bomb paper in Nature, and then it was shown in 2015 by Shlapentokh-Rothman. So superradiant instabilities do happen. The fact that you have their ergo region and the possibility of the Penrose process, this can lead to having unstable mode solutions to your equation. Okay, it is possible. And so they were worried about this, and they looked numerically at these at the possibility of this happening. So they write no instabilities. So they looked by numerical integration of the separable to perturbation equations for the Kerr metric. So exactly what I wrote here. No instabilities are found in any of the dozen or so lowest angular modes tested for any value of specific angular momentum. These results add credibility to the use of the Kerr metric in detailed astrophysical models. Now, since this paper of Professor Teukolsky, I think many people have credited them with solving the black hole stability problem, because they write, you know, they've looked for unstable solutions and they couldn't find any. But, you know, for us mathematicians, this is still a little unsatisfying. And I think Press and Teukolsky were not satisfied themselves. Their abstract is quite toned down. So they do not in any way claim to have solved the problem of stability. They simply say, we haven't found any unstable modes, and this somehow adds credibility to the use of Kerr, although, you know, the jury is somehow still out. Okay, so for us mathematicians, now the task is clear. You want to show that solutions to the Teukolsky equation remain bounded and in fact decay in time. So you want to show that these unstable modes don't exist, and you want to even show that they decay in time, so that, you know, as time goes to infinity, you are approaching more and more the value of alpha on the particular on the Kerr background, which is 0. Okay, hopefully this makes sense. Okay, so how does a mathematician now approach this? Well, informally, okay, this is not rigorous. A solution to the Teukolsky equation we expect is sort of like an infinite superposition of these separable solutions. And maybe now I can go a bit slower and explain what are the things going on here. So omega is a time frequency, m is an azimuthal number. And the fact that you can separate these out, this just follows from somehow from the fact that you have a stationary killing field, the d by dt, and you have axisymmetry of Kerr. And then the non-trivial part aspect that I mentioned is the separation of the r and theta variables. So here you see the r and theta variables coming out separate. And the separation constant is this capital lambda here, okay? That's the notation that I'm using. There's a separation constant. So for instance, if you were on Schwarzschild black holes, you would have a spherical symmetric spacetime. The separation would be pretty obvious, and the lambda would just be L times L plus 1, like in the spherical harmonics, okay? If that makes sense, okay? So you should think of lambda as a generalization of that, because now you no longer have spheres, you have sort of ellipses. And because you have ellipses, the lambda is not going to be so easy to write down. In fact, it will depend on A times omega, okay? So in this infinite superposition, again, I'm going more slowly over this. So U here and S, they satisfy ODEs. The S satisfies an angular ODE, which mostly I don't care about, but it's kind of an ODE that constrains the value of the separation constant lambda. And U satisfies a radial ODE, which I very much care about. And because I care about it so much, I'm going to show it to you. So the ODE looks like this. It's like a 1D Schrodinger equation, okay? U double prime plus V omega squared minus V times U equals 0. So really, I'm writing this in Schrodinger form, right? So I have second derivative, I have here an energy level, and I have some potential, okay? And the potential is not super nice looking. So here's the potential. You can write it explicitly in terms of the Kerr parameters, MA. So delta, if you remember, was also a function of R, which depends on the Kerr parameters. And you can write it explicitly in terms of the frequency parameters as well. So you see here omega, the time frequency, you see the azimuthal number M, and you see this separation constant capital Lambda. Okay, and okay, here the prime is a derivative with respect to the so-called tortoise coordinate, which is a coordinate, which is a rescaled radial coordinate. So we're working in the Kerr exterior, so we're going between between R plus the value of the event at the event horizon and infinity. But now here we are rescaling that so that infinity stays at infinity, but R plus the value of the event horizon gets mapped to minus infinity. Okay, and so this is what the potential looks like. Now we can hide it again. So what does a mathematician want to do? Well, we don't actually want to just exclude non-zero solutions which have positive imaginary parts. Remember, those are the ones that Teukolsky and Press were trying to exclude because they corresponded to exponentially growing in time solutions. So it makes sense to want to rule that out. But actually for us, we actually want to also be able to rule out solutions which have omega on the real axis. Why? Because if you think about it, if omega is on the real axis, these are just solutions which are sines or cosines. So they are bounded, but they're not decaying in time. Okay. And we would like at the end that our solution to the Teukolsky equation is something which is decaying in time. And in fact, us mathematicians have a way of just being able of making do with this last statement. So if you can show that you can rule out solutions which have omega on the real axis, then you're done. Okay, we can have a proof which only needs the information on the real axis. And this is actually quite fortunate because this separation makes perfect sense if you are on the real axis. So these angular functions will form a complete basis if you're on the real axis. But if you're on the upper half plane and you go away from the real axis enough, suddenly there will be problems with your angular ODE, branch points, et cetera, which make things very nasty. And it's not clear that when you look at the complex plane that the angular functions form a complete basis. So it's not clear that you could make sense of this statement here, this informal statement that a solution is this infinite superposition. You can make sense of it in the real axis. And that's why it's very fortunate that for us mathematicians, we have a way of just using the real axis. And it's really not surprising that we have a way of just using the real axis. It's just a Fourier transform, right? So that's all that we're using here. And you don't need, to understand Fourier transforms, you don't really need to go to complex values of the Fourier parameters. Okay. So omega is on the real axis. And now let me tell you more concretely what we want to show. What we want to show is, and there's many words here, a quantitative uniform in frequency non-existence of non-trivial solutions of the Teukolsky equation with good boundary conditions. So let me break that down for you, starting with the end. Good boundary conditions what do I mean by this? Well, we want to be studying solutions of the Teukolsky ODE, which arise from physically reasonable solutions of the Teukolsky PDE. So physically reasonable solutions of the Teukolsky PDE should be sort of ingoing at infinity. Outgoing at infinity, at infinity, and ingoing at the event horizon. And we just want to carry so that they have finite energy. So that this idea is something that we want to carry over to the Teukolsky ODE. So we have a second order ODE. In order to study it, we need to specify boundary conditions. And there's an obvious definition of what should be the good boundary conditions, which comes from looking at the Kerr geometry and figuring out what are the physically reasonable solutions. Okay, so that explains the good boundary conditions. Now, why we want to show non-existence of non-trivial solutions, that I've already said, right? So we want to rule out solutions which have omega real. But now, why do I want to do this in a uniform and frequency way? I want to do this in a uniform and frequency way because you have to imagine that I have here an infinite superposition. So it's not enough to rule this out, for it's not enough to say fix omega, then the only solution is 0. I actually have to be able to say that this still holds when you reach arbitrarily large omegas, because my infinite superposition is going to involve arbitrarily large omegas, ones which you cannot simulate on your computer. Okay, so I want to show this in a uniform and frequency kind of way, and I want to do quantitative statements. This is a bit more this is a little harder to explain for non-mathematicians, but basically the idea is that I want at the end of my day not to just have the statement that they don't exist, but actually to have an estimate that tells me by how much they don't exist. And I want that by how much they don't exist to be explicit in the black hole parameters, basically. So that at the end of the day, when I prove stability of Kerr, which I doubt that it will be done, by me in my lifetime, but once this is proven, you want the stability to say, consider that you're sufficiently close to Kerr and that sufficiently close being measured explicitly in terms of the Kerr parameters, then you will converge to a Kerr solution. Okay. So let me start trying to now explain how we go about doing this, how we go about showing the quantitative uniform and frequency non-existence of non-zero solutions. And I want to start by kind of throwing away that word uniform, which maybe you didn't like, and actually be more in the setting of the fixed frequency case, which I said we would need to go beyond. But let's start with that case. That case is basically what Teukolsky and Press are doing. What we are able to simulate in a computer is something like this. It's fixed frequency. We cannot go all the way to infinity. Okay, so let's start with the fixed frequency. So we fix some omega, we fix some time frequency omega, we fix an azimuthal number m, and we fix a separation constant lambda. And now we asked, are there non-trivial solutions of Teukolsky ODE which have good boundary conditions? And there's actually a very systematic way of answering this question in general. And that systematic way is to find a quantity for our ODE, which is both conserved and coercive. And on the conserved side, we have very good news. So this is something that you've seen already at the beginning of my talk, and now I'm talking in more detail about it. So on the conserved side, we have very good news because we have a stationary killing field, and that stationary killing field induces an energy which is associated to the stationary killing field, in which you can write in terms of my ODE notation like this. So this is a conservation law. You have 0 equals something, and that something is boundary condition at infinity multiplied by some factor, and plus boundary condition at minus infinity, meaning the horizon, multiplied by some factor. Okay, and now this factor is written in terms of omega and the azimuthal number m explicitly, and we have here this definition of omega plus explicitly in terms of the black hole parameters. Okay, so we have a conserved quantity. Now, is this quantity coercive? Coercive means, does this quantity control the solution? And we see that actually it's not. It's not because it's not in general, okay? Because if this factor here, omega times omega minus m omega plus happens to be positive, then yes, we do have coercivity. We have coercivity in the following sense. So if this factor is positive, we have boundary condition at infinity squared times something positive plus something positive times boundary condition at the horizon squared. And the only way that this can be equal to 0 is if both of the boundary terms vanish. So the only way that this can be equal to 0 is if u is 0. So in that case, we have answered this question in the negative. There are no non-trivial solutions. And moreover, we see that this conservation law, it really controls our solution, okay? So it tells us, it gives us this very, very, suddenly you just know that this guy is positive, and suddenly you're able to say by this conservation law, u has to be 0. Okay, so it's really controlling our solution. But if this guy is not positive, if it's negative, then what you have here is the boundary term at infinity competing with the boundary term at the event horizon. So they could be both very, very large as long as they cancel each other out. So it's really not controlling your solution at all. You are not able to say anything about your solution, but if you have this condition. And this condition, you've seen it before, it was called superradiance. So if you want, every time that I say coercive, you can replace it by non-superradiant, okay? And you see that this is obviously very problematic in the case of rotating black holes. So if you don't have a rotating black hole, then this guy will be 0. So you'll just end up with omega squared here. And so you'll always be in that first case where you have positive times boundary term, plus positive times boundary term. You'll always be in the case where you do have that control over your solution. So it's really just in the rotating case that you have this problem. Superradiance is just a property of the rotating black holes. You don't have an ergo region in Schwarzschild. You just have an ergo region in Kerr. Okay. And as I've told you before, in general, ODEs are going to be modally unstable. So I've talked about the case where you have a Kleingordon mass, which was shown by Shlapentokh-Rothman with many, many people before doing heuristic and numeric arguments. You can also show this if you, instead of adding a mass, you just add a potential which is compactly supported away from the event horizon and away from infinity. And this was shown by Moschkidis in 2017. But for the Teukolsky equation, there's a kind of algebraic miracle. Even though you expect that generically you'll have mode instability, for the Teukolsky equation, there's an algebraic cancellation which happens, which somehow magically tells you that there will be mode stability. So it tells you that the answer to this question here is no. Whenever you are looking at solutions of the Teukolsky ODE which have good boundary conditions, they're going to have to be 0. Okay. So we fix omega m lambda, then the only solution with good boundary conditions is the 0 solutions. And this is the case for sub-extremal Kerr, and it's also the case for extremal Kerr if you additionally eliminate this funny frequency. Okay, and there's just a little note. I said that it was important not to just have a non-existent, a soft non-existence, but to actually say by how much do these things not exist. And that's exactly something which is done by Shlapentokh-Rothman for waves, and which I did for the general spins in 2019. Okay, so this is obviously a very important statement because this is the proof of what Teukolsky and Press were grasping at in that paper. So if you take nothing else from this talk, please take away the idea that it wasn't Teukolsky and Press that proved stability of Kerr, it was whoever proved mode stability. And these are, I'll tell you in a second who these people are. So how does the classical proof of mode stability go? So this is by now a classical result, and the classical proof is as follows. So I said that there was this systematic way you find a conserved non-superradiant quantity, okay? There is a way of sort of cheating that system, if you want, which is to say, well, I can't find that for my original equation, but I'm going to find another equation which is isospectral to my equation. So it has the same, if you want, quasi-normal modes, has the same mode solutions, has mode solutions for the same frequencies. I'm going to find something which is isospectral. And for this isospectral thing, this TO tilde, I'm going to show that there is a conserved coercive quantity. So the way that this will work is I'm going to say, okay, for TO tilde, since I have a conserved coercive quantity, I will have no mode solutions on the real axis. We'll have no modes on the real axis, and by the isospectrality, that implies that I'll have no modes for the Teukolsky equation. So the classical proof gives you basically an idea of how to construct this isospectral equation. So the classical proof is you take this, you take some u tilde to be an integral of u against some kernel. And here I'm just going to add a weight here, w, so that tr is self-adjoint in L2w, which just means that when I put tr here, I'm going to be able to swap it. So suppose that you are given, so this is just the definition of some u tilde. Now, suppose that you are given a differential operator, t tilde, which satisfies this property. So tr here is just the operator associated to the Teukolsky ODE. So, and suppose you're given this t tilde, which satisfies t tilde minus tr applied to that kernel equal to 0. Then you can show that the equation for your u tilde will be t tilde u tilde equals 0. So it's easy to see why. So, you know, this is all back of the envelope computation. You put t tilde here, and now you put it on the inside. And when you put it on the inside, you add and subtract tr. Okay, so t tilde minus tr, and here tr. Now this term disappears because of the condition star that we impose. And the first term here, it's going to, you can use the self-adjointness of the weight to say, to place the tr not on k, but on u. Okay, so this is equal to the same thing with tr now on u, and the equation that u satisfies is tru equals 0. So now you see that you have t tilde u tilde equals 0. So you have this way of producing an equation which, you know, so you have this way of, you know, taking your equation and producing a new equation. And now you want to show two things about this method. You want to be able to, this method to work for your setting. So you want to guess an integral map, this integral map, you want to guess a kernel K, which allows for you to have injectivity. Because if you have injectivity, then they will have the same, then they will be isospectral. They will have the same quasi-normal modes, okay? And you also need to guess, so I said that you have to be given a t tilde. So you also need to guess this t tilde. You also need to basically guess what will be the new equation. And you want that guess to be very good because you want that this new equation has a conserved coercive quantity. So you want it to not have any superradiance. Okay, and this is really, really done by guessing. And the first guess of how this was done was by this absolutely incredible work of Whiting in 1989. So again, if you don't take anything else from this talk, please take away that it was Whiting. You know, if you want to claim that someone has solved the black hole stability problem, please give this honor to Whiting, because he came up with some amazing guesses of what should be the kernel, what should be the t tilde, which allowed him to show that the thing that Teukolsky and Press were grasping at is true. If you fix omega, m, and lambda, so if you fix a set of frequencies, then the only non-trivial solution with good boundary conditions is the trivial one. It's the 0 solution. Okay, so Whiting did this for sub-extremal Kerr, and then in 2019 I did the same thing. So I had to come up with new guesses for what the k and the t tilde should be in the extremal case, because Whiting's transformation, it really breaks down in the extremal limit. So when you look at the extremal case, you have to make completely new guesses, and it turns out, you know, when you look at these proofs, it turns out that the correct choices are to take a kernel, which is kind of an exponential, and to take t tilde to be a confluent, something called a confluent Hoyne operator. I won't go into this very much, but you know that this is, it turns out from these two papers that this is the right thing to do in Kerr spacetime. And the reason why this is very hard is because these choices are really fine-tuned to the spacetime. So for instance, this xi here, it's normalized with respect to the Kerr parameters, and it's discontinuous when a goes to m. So in Whiting's case, it blew up in the extremal limit, and that's why you needed a new set of guesses in the extremal case. You need a new set you need a new kernel, and you need kind of a new form of this confluent Hoyne operator. Okay, and moreover, this is really, really annoying to implement if you are looking at real omega, which, as I said, us mathematicians, this is what we're interested in. So Whiting did this in the upper half plane. He did this for the unstable modes that Teukolsky and Press were also considering. But mathematicians, we want to do it on the real axis because we have a way of, using real axis to infer a result. And if you want to apply this method on the real axis, then you need a regularization argument. And the reason is very simple. If you take an exponential kernel like this, and if you imagine that C is like omega, if omega is on the real axis, then is on the upper half plane, then this will give you exponential decay. So here, all of these back of the envelope computations that I did, they will be easy to justify because the kernel has exponential decay. But if omega is on the real axis, you won't have that exponential decay. So all of this will be harder to justify. And that's why you need a regularization argument, which is quite annoying. Okay, so let's see, I don't have that much time already, but I'm through with half of the slides. So, okay, so you see, there are reasons to sort of hope that you could have a different proof of this very classical result of mode stability. And here is a new approach, which is joint work with Marc Casals, who is at Centro Brasileiro de Pesquisas Físicas and University College Dublin. So the approach is really to go back to the classics in every sense of the word. So this is a paper which, if you're familiar with black hole perturbation, you've seen many, many times. This is Lever's paper for quasi-normal modes on Kerr black holes. And what he does is he gives you a condition for the existence of a mode solution, a non-trivial separable solution with good boundary conditions. Okay, so he says that a non-trivial mode solution exists if the frequency omega is a root of a certain continued fraction equation. And so how is this a continued fraction equation? First of all, well, it's a continued fraction equation because you have to imagine that this guy is after the minus and this guy is after that minus. So if you're not familiar with math notation, that's how it works. The way and these coefficients, alpha, beta, and gamma, they are also explicit in the black hole parameters, and they're explicit in the frequency parameters. And here they are. So alpha has this horrible expression depending on the index n, which appears here in the continued fraction equation, and on some intermediate constants, which he gives here. And maybe you'll notice that capital M, the mass of the black hole, is absent. That's because he uses the very unfortunate notation that M is equal to 1/2. But really it's hiding here. So this ALM is my lambda, my separation constant, basically. So you have this very nasty expression, and you can ask, well, how does he get this? Well, he gets this basically by doing decompositions of the solutions of the ODE with respect to a basis of special functions and trying to enforce the boundary condition. So in 2 minutes, that's what he does. So when he plugs in these expansions for the solutions, he gets a 3-term recursion relation. These are the recursion coefficients. And when you solve that recursion relation, you will get this continued fraction equation. Okay. Nice. Okay. So one way that you can kind of think about proving mode stability, if you have this, is, well, this is a condition for existence of a non-trivial mode. So if you can just show that this condition, this continued fraction equation, has no solutions on the real axis, for instance, you're done. Or on the upper half plane, you're done. You have managed to show this theorem, which I said was so important. There's a problem with doing that, of course, and the problem is you look at this page and you don't want to do it because the intermediate constants here, in theory you can do it, but in practice, how are you going to deal with the fact that you have all of this complexity here going on, right? It's not easy to show that there are no solutions to this continued fraction on the real axis, especially when the dependence on the omegas is so complicated. The dependence of alpha, beta, and gamma on the omegas is so complicated. Okay, so here's an idea. Maybe the reason why this looks horrible is because Lever chose the wrong kind of intermediate constants to consider. Maybe if you come up with a clever idea of what the intermediate constants should be, things will look nicer. And so with Casals, we introduced this idea for the intermediate constants. So we call them masses M1, M2, M3. They're again completely explicit, okay? And S, M, omega, little m, A, etc. And it turns out that if you plug in these intermediate constants, then suddenly the coefficients in the continued fraction equation do turn out to look much, much simpler. So Lever wrote alpha and gamma independently, since in the continued fraction equation, which is what I'm interested in, alpha appears always multiplying gamma. I'm just going to put the product here. And then I'm going to look at this, and I'm going to look at beta. And now I'm going to write it in terms of my intermediate constants, and this is what I get. So what I find is that the dependence on these masses, which I introduced, is only through the so-called symmetric polynomials. So sigma 1, sigma 2, sigma 3. Sigma I means symmetric polynomial of degree I. So sigma 1 will be M1 plus M2 plus M3. Sigma 3 will be M1 times M2 times M3, okay? Third degree. Okay, and so this already looks much, much nicer. So it's shorter than this for sure. And so on the surface, this might seem like it's just a cosmetic improvement, but in fact, it's much, much more, because since I'm writing here, since it turns out that the dependence on the recursion coefficients their dependence on the intermediate constants is only through symmetric polynomials, what that means is that the continued fraction equation is invariant under swapping any of these masses. Swapping M1 and M2, swapping M2 and M3, swapping M1 and M3, all of this will lead you to exactly the same continued fraction equation. Okay, and let me tell you why this is interesting. So let me just write again that Teukolsky ODE, which I showed you before, that Schrodinger type ODE with a very explicit potential. This looks horrible with the potential written like this, but now I've introduced these intermediate constants. So let me take advantage of that to write my potential in a somewhat neater form with these intermediate constants. Okay, so what do I see here? Well, if I change M1 and M2, nothing changes. The potential is the same, because you see the dependence on M1 and M2 is very simple. But if I change M1 and M3, or if I change M2 and M3, suddenly something different is going on, right? And what I said before is that, so the condition for existence of a mode does not change, but the equation does change. So that gives you now a new idea of how to come up with how to produce from your equation a new equation, okay? And this new equation that you produce when you apply the symmetries will be isospectral, because we just showed that the continued fraction condition, the condition that tells you if there's a mode, is invariant. So I've shown that the condition, the quasi-normal mode spectrum, if you want, has symmetries corresponding to exchanging M1 and M3 and corresponding to changing M2 and M3. And changing M1 and M3, actually, you can see very easily here, is trivial. It's just swapping the sign of S. And that symmetry we know. This is the Teukolsky-Starobinski identities, which are very familiar in the physics literature. They go back to the 70s. But exchanging M2 and M3, this is more interesting. This really drastically changes the equation, okay? And it turns out that what this does is that it recovers Whiting's ODE. So without having to do an integral transformation, we have arrived at exactly the same ODE as Whiting did in his paper. And that is an ODE which has a conserved coercive quantity. And since that ODE has a conserved coercive quantity, it has the property of mode stability. And by the isospectrality, we conclude that, that we have mode stability. And all of this without having to go through Whiting's integral transformation. So this is a different way of generating that isospectral equation to reach mode stability. And I should point out that this theorem here, this was conjectured by Aminov, Grassi, and Hatsuda, who really came up with this idea of writing the Teukolsky equation in terms of these masses. And they came up with this idea by comparing the Teukolsky equation with some equations arising in supersymmetric quantum chromodynamics. So maybe the high energy physicists will be happy to hear these words now. Okay, so this is one advantage of this method, is that we don't have to do the Whiting's integral transformation. Another advantage is that it turns out that it's more flexible. So as I said before, the Whiting this method, the classical method of guessing the kernel and guessing a T tilde, this is very rigid. You see, I said that the choices that we have to make are always very fine-tuned to the space-time. And so it's very, very, every time that you encounter new space-time, you have to start from scratch. In contrast, this method of finding these intermediate constants, it's more flexible. And to showcase this, we are able to look at sub-extremal Kerr de Sitter, for which no analog of Whiting's result exists. No transformation has been proposed, and which works, okay, has been proposed. And so we look at sub-extremal Kerr de Sitter, and now we select some masses, some intermediate constants, which are not 3 but 4. They are again explicit in the black hole parameters and in the frequency parameters. So kappa here is the surface gravity at some horizon in Kerr de Sitter. Omega plus is the angular velocity at that horizon. And again, we can show that the Teukolsky ODE has these spectral symmetries of exchanging the masses. And exchanging the masses is a symmetry of the spectrum, but it's not a symmetry of the equation. And since it's not a symmetry of the equation, we actually can show that mode stability holds for some subradiant frequencies. The match is not perfect as in Kerr. So in Kerr, we are able to then show mode stability for all subradiant frequencies. Here, we are only able to rule out the subradiant frequencies which lie in this orange region, okay? So it's still an open problem to understand what happens in the blue region. It's still an open problem to decide whether Kerr de Sitter is modally stable or not. Okay, so we are progressively getting more hardcore. And now I think we are getting to the most hardcore, which I've titled painful but necessary. So I said at the beginning that we need to prove non-existence of the non-zero solutions in a uniform and omega way. And the reason why is because we had that superposition, that infinite superposition. And we need to make sure that when we look at infinite omegas and m's and lambdas, we need to make sure that, we still have no modes. So that's just a text here again. And through mode stability, and I just want to emphasize again why the mode stability doesn't give us this, because mode stability, what it says is fix an omega, then there are no modes. So basically, you can pick a very large box of omegas, but you can't go all the way to infinity. So mode stability tells us, fix a very large box, whatever box. You can fix any box, but it will be a box. Then there will be no modes in this blue region. And of course, you have to exclude the zero frequency. I don't know if I mentioned this properly, but in the mode stability statement, you have to exclude the zero frequency. The proof does not work at the zero frequency. So you have very close to zero, this doesn't work. And I did mention that for extremal Kerr, very close to this other funny frequency, it did not work. Okay, so through mode stability, we know that we have this huge space where there's no modes, but we still don't know, okay? And we still have to prove that there can be no modes coming in from infinity, right? This is the uniform and omega part. And we also need to make sure that there are no modes coming in from that zero that we excluded, from the zero frequency that we excluded. And if you're interested in extremal Kerr, then you have to make sure that there are no modes coming out from this cut right here, okay? That's what we need to do in order to show stability of Kerr, okay? It's not enough to do mode stability. However, this, in some sense, is much easier. In the following sense, okay? So you look at this equation again. It can be this, so this one. If I tell you that omega is very large, then for instance, that this term here, s squared, this s squared term is completely irrelevant. If omega is very large, you know that you don't care about the entire potential. You just care about some part of that potential. Similarly, if omega is very small, you can throw away a bunch of terms here, okay? So if omega is very large or very small, we as mathematicians or physicists, we have arguments to say, well, the only part of the potential which will matter will be this one. And now we can just do analysis. We can just analyze what can happen with that kind of potential. If the potential has a simple form, with our first course in quantum mechanics where we learn to deal with these equations, we might be able to figure out what's going on if the potential is simple. So in that sense, it is easier to deal with. It is easier to deal with the limits where omega is very large or omega is very small. in some sense, what is hard is to deal with in just the sense that we don't know what to do. It is harder to look at the case, the mode stability case, where omega is neither small nor large, and we can't throw out any part of this potential. Okay, so I want to tell you that, you know, this is in some sense easier in the sense that we have strategies to deal with it. We can throw away parts of the potential. We only care about the leading order terms, and we have strategies to deal with the leading order terms. It's for the mode stability range, which we really have no good concrete strategies, as hopefully I illustrated by, you know, the big question marks that corresponded to that part of my talk. Okay. So it's easier, but at the same time, it's very, very painful, and it takes many, many pages to do, because if you want to rigorously justify that intuition that we all have, that you only care about the leading order part of the potential, and that leading order part is going to behave in a certain way, to justify this, it's still going to take you a lot of work. Okay, and this big task of going through this boring stuff, this was done. This was something that I did with Shlapentokh-Rothman in 2020. So what we show is that there are no modes coming in from the high frequencies, or no modes coming in from the omega equals 0 frequency in the full subextremal range as a smaller than m. Okay, and so combining that with the mode stability result, you can show that solutions to the Teukolsky equation are bounded and in fact decay in time. And of course, you know, the way that I'm presenting this, it sounds like we were the first to come up with this, but that's not true at all. So this is, we're really standing on the shoulders of giants, so to speak. Our work comes after decades of work on the Teukolsky equation, and on showing this kind of boundedness and decay in time. And this is a picture illustrating just that. Okay, so of course, people looked at this very much for the Schwarzschild case. And you know, this was fundamental to us, especially this work of the Fermos, Holzigel, Rodniansky. And it is also fundamental that people have studied this problem in the case where you're looking at scalar waves, s equals 0, in the Teukolsky equation. So that was a much simpler form of the Teukolsky equation. And that study in the full subextremal range was done by the Fermos, Rodniansky, Shlapentokh-Rothman back in 14. So somehow it is by drawing very heavily on both of these works that then we're able to show this result. Okay. And so these works I've mentioned here, the Fermos, Holzigel, Rodniansky, and Taylor. But I want to also mention that looking at the Teukolsky equation, I just want to bring back that point that studying the Teukolsky equation, this is the first step to understanding stability of Kerr. And in fact, these works on the Teukolsky equation have paved the way for people to show, for instance, decay of the linearized Einstein vacuum equations when the Kerr black hole is very, very slowly rotating. This was done by Anderson, Bakdal, Bluma, and Hafner, Hintz, and Vajee in 2019 to study, you know, coupled electromagnetic and gravitational perturbations. This is work done by Georgi, et cetera, et cetera. Okay, so this really is the first step, is understanding the Teukolsky equation, in proving this statement. Okay, and this statement, as I said, it not only entails mode stability, it entails something which is painful but necessary. And I want to tell you a little bit about that painful but necessary part in the 5 minutes that I have left. Okay, so blazing through it. So let me start with the limit where omega goes to 0. So in the limit where omega goes to 0, you actually have something quite bad in your potential. If you look at the potential again, you will see that if omega is very small, but it's non-zero, then this term here does not vanish. And this term is a long range part of your potential. And it's a long range part of, it's part of the, your potential has an imaginary component, which is long range. Both things are awful, and I think they have been identified as being awful by people who do numerics as well. You don't want long-range potentials in general. So there's many works in the literature about how to get rid of this long-range potential by kind of considering, again, transformations from the Teukolsky equation to some other equation which does not have this longer range potential. A little bit like in the mode stability, but typically people consider different types of of transformations. So the transformation that we will use, it's something which was done by the Firmus, which was also used by the Firmus Holzigel-Rodniansky, is something called the Chandrasekhar's transformation. So basically, you take new variables which are null derivatives of your Teukolsky variable in the right null direction, okay, and you find that if you do this s times, S being your spin weight, so plus or minus 2 if you're looking at gravitational perturbations. So if you do this twice, in the case of gravitational perturbations, the new variable, the Chandrasekhar variable, satisfies a new equation which has a real potential. The imaginary part is gone, and also it's short range, so it goes like 1 over r squared. Okay, so that's really important in the low frequencies. This is an idea which is really important. Now let's look at the high frequencies. Well, the high frequencies, you see something appearing in Kerr, which I haven't mentioned at all before in this huge talk about Kerr. So I mentioned superradiance, but I never mentioned trapping. I never mentioned any photon spheres. Now is the time when photon spheres appear. If you're looking at the very large limit of frequencies, then you can have trapping. And this new potential that comes with a Chandrasekhar transformed variable, this really is like the scalar wave. So you have a kind of trapping at high frequency. You have this kind of photon sphere. Now, in Kerr, this is not really a photon sphere. It's more like a photon region. It's thick in R, unlike in Schwarzschild, where it really is a sphere. And it comes in addition to the problem of superradiance. So this photon region intersects the ergo region. So you could be worried that you have trapped waves which are undergoing that Penrose process that I called superradiance. So somehow they are trapped without being able to go into the event horizon, go into the black hole, or escape to infinity, and they're always interacting with the ergo region and maybe gaining more and more energy. So that can really worry you. And because when you look at the geometry, it does look like these two things are coupled. The trapping set intersects the ergo region. However, when you look in the ODE world, suddenly you see that, thank God this doesn't happen. In the ODE world, you recover a photon sphere, so you don't have that thick range. So there's a single R value for each omega m lambda for which you have trapping. And moreover, if omega m lambda is superradiant, then it cannot be trapped. So you can show that if you are undergoing the Penrose process, you cannot be trapped, which is very nice. Okay, so it prevents that situation that I said, where you have accumulation of energy. Okay, and this observation was first done by the Firmus Rodniansky in 2009 for slowly rotating black holes, and then it was shown in the full subextremal range by the Firmus Rodniansky Shlapentokh-Rothman in 2014. So this is another place where we really draw on this earlier work. Okay. Let me just finish with this. So in the high frequency, maybe I didn't mention this enough, but when you do this Chandrasekhar transformation, there are no free lunches. So when you do this Chandrasekhar transformation, yes, you got rid of your imaginary long range part of the potential, but you will get a right-hand side. So you will no longer have a decoupled equation. You will have here some coupling to what? Well, to all of the lower order Chandrasekhar variables. So to the Teukolsky equation and some of its derivatives, okay? Of course, notice that as usual, there will be a free lunch if you're looking at Schwarzschild, not just in the issue of not having superradiance, but also you won't have this right-hand side if you're looking at Schwarzschild. So it's really a Kerr issue. It's really a rotation issue that you have this, you have to pay this price. Okay. But we are interested in rotating black holes. We know that rotating black holes are out there, and so we are willing to pay this price. This price, what it tells us is that the analogy between this new Chandrasekhar variable and the scalar wave setting, it will not be perfect. It will not be perfect because we have something here, not zero. Okay. And one way that you can see the imperfectness of this correspondence is to compare definitions of energy that you can take. So one definition of energy is a definition that you take for scalar waves. So scalar waves, this is the definition of energy which has appeared before. It's the energy associated to the d by dt killing field. There's a very concrete way of writing that. If you now translate the formula that I gave you before for U to psi, this is what it looks like. So this is exactly that same expression that you saw before, but now because you have a right-hand side, you won't have a conservation. You will have this right-hand side here, okay? So you can compare this with another notion of energy, which is the notion of energy introduced by Teukolsky and Press to look at specifically spin-weighted fields. So the solutions of the Teukolsky equation. So this is actually, so this will be, of course, since it was an energy designed for the Teukolsky equation, it is an energy which is conserved. But if you notice, so you have equals to 0. But if you notice on the left-hand side, what do we have that is equal to 0? You will see that somehow it doesn't look like what I showed you before. Now there's these additional terms, these strange additional terms, CS over ds. And these are some constants which are, again, explicit in the black hole parameters and the frequency parameters. Everything is explicit here. However, you know, explicit though they may be, they're still very bad. And they're bad because it can be degenerating in some parts of the frequency space. So for very large omegas, some region of the very large omega space, some region of infinity, they are going to 0. So you're losing control when this goes to 0. You lose control over the boundary term at infinity, right? This identity loses control, and it only gives you control over the boundary term at minus infinity. So that's kind of annoying, you know. Comparing to the killing energy, you have good frequency weights. So you have to kind of balance when you do all of this analysis, you have to kind of balance. Sometimes you're going to have to, sometimes you can deal with these frequency weights which behave weirdly. And so you'll want to use this energy, but sometimes you can't deal with those frequency weights. And so you'll have to use this other energy. And so you'll have to deal with the fact that it's not conserved. So these kinds of things, they really complicate the analysis. But at the end of the day, it is possible to use all of these ingredients to get a proof. And, you know, I said that I would increase in horribleness as we reach the end of the talk. So this is just a simplified picture of what that analysis actually entails, of how we divide up the space of very large frequencies and very small frequencies to do our analysis. And I think that's a very good place to stop. Thank you.
Thank you, Rita. Thank you for this very nice talk. Let me see if we have some questions. If someone here in the Zoom talk, in the Zoom call wants to ask a question, well, I go to YouTube. So we have one says, hi, Rita, would the gravitational waves emitted by this type of black holes carry relevant information about the stability? And if so, could we hope to measure it in an experiment setup?
Yes, I think so. And, you know, all of these, the gravitational waves, they're all, this, you know, in the Teukolsky equation, all of the things that LIGO is picking up, if I understand correctly, and if I don't, then Alejandro will correct me, as he has before. You know, when you look at what LIGO is picking up is the alpha minus 2 component of this Teukolsky master equation. So yes, definitely. But, you know, I should point out that it is definitely an expectation that Kerr is stable. I mean, one of the reasons why we use it as an astrophysical, I mean, there's two reasons why we use it as an astrophysical model. One is that we think that it's the only black hole which is stationary in 4 dimensions. So if you want to have a stationary state, which is a black hole, it has to be Kerr. And there are some uniqueness theorems that support this claim. Although for mathematicians, you know, there's still some work to be done on the assumptions of those theorems. So that's one reason, is it's the only black hole which is stationary in 4 dimensions. And the other reason is we think it's stable. Because, you know, if we didn't think it's stable, then we wouldn't use it for astrophysical models. So yeah. So as far as I know, no astrophysicist doubts that black holes are stable. Kerr black holes, at least in the sub-extremal range. I don't think that anyone doubts that they're stable. And I'm sure that there's lots of numerical work which is much more convincing than this paper of Teukolsky and Press, which I showed you. This was really the early tests of stability.
Okay, yeah, I think related to that, there was another question that maybe you sort of address it here. It is, computer might not be able to provide a proof, but maybe a counterexample or something like that. What does the numerics tell us about the stability of Kerr black holes?
Yeah, I think the numerics tells us that they are stable. But again, I think you, Alejandro, are more apt to answer this question than I am. Certainly, since this paper of Teukolsky, many people have computed numerically the quasi-normal modes, and I think, okay, quasi-normal modes means solutions of this equation, means solutions like this when omega is in the lower half plane, imaginary part negative. But whenever they do these searches, whenever they can do these computations, as far as I know, they also keep in mind, they also check just to be safe that there's nothing in the upper half plane, nothing on the real axis. So there's definitely, but since the 70s, there's been big advances in computing. So I do think that the state of the art in terms of numerical tests is much better, and not just from the point of view of the Teukolsky equation, but probably full Einstein equations, right?
Yeah, cool. Thank you. Someone here in the Zoom call wants to ask a question.
Yes, I have a question for Rita. Very nice to talk, Rita.
Thank you.
My question is regarding with this photon region that you were mentioning at the end of your talk. In the sense, because of the nature of the Kerr black hole, is it possible to, in the observation of these photons coming from the photon region, not the photon sphere, to have a special signature with respect with other type of black hole, like in astrophysical environment? Because I remember the imaging of the black hole that they observed with the radio telescopes, that there were photons that were trapped, and then you can have this ray tracing, and you have the special shape. If it is in the case of the Kerr black hole and this region, to have a special, how to distinguish the two different black holes, or see if it is rotating a lot or not so much.
I don't know exactly, because this is not the kind of thing that I work on. I think Alejandro, again, will be able to answer this question better. I do think that for the question of rotating more or rotating less, there probably is some connection. You can probably see this from the ray tracing. Is that wrong, Alejandro?
Yes, yes. Although, like, we don't have enough the resolution to.
Sure. I mean, in practice, no, but simulation-wise, you can definitely tell the difference. I think to distinguish Kerr from a different type of black hole, that would be seems like it would be much more difficult, because you're not getting a full image of the Kerr black hole by doing the ray tracing. So I don't see why there should be some uniqueness. You see why the image that you get by ray tracing should be uniquely characterized Kerr, why you shouldn't be able to construct some other geometry which gives you the same. I think that there are some people who do work on this type of problem, like trying to come up with geometries that have the same ray tracing, have the same image when ray traced than Kerr is.
We have a law physics webinar like in last December, I think, like someone talked about this type of mimicker. So for the audience that wants to, they might want to revisit that video. Okay.
Yeah. So and another question that's very small. I mean, also related with this part of what is kind of the implication in the case of Hawking radiation, if it in the case of this deformed region makes is evaporate faster or slower with respect with the non-rotating black hole?
This is a question which I definitely don't know how to answer. I don't know. You see, well, I did part 3 in Cambridge, as we were discussing before the seminar. And obviously we do talk about Hawking radiation, but it's very conspicuous that whenever you talk about it and whenever you sort of, actually do the computation, suddenly you're in Schwarzschild. You're in a kind of Oppenheimer-Snyder-like space-time, which is like Schwarzschild. And actually, there's another student of my advisor who was PhD student, same time as me, who was working on the problem of scattering on Oppenheimer-Snyder space-time, precisely with the goal of understanding Hawking radiation from a more mathematical perspective. But you see, when you look at rotating black holes, there's no Oppenheimer-Snyder. So I have no idea how I would do that computation. And I don't know how people think about doing that computation for rotating black holes. I'm sure that there are back of the envelope arguments involving black hole thermodynamics that tell you something, but I don't know. I have no idea.
Okay.
And also
because I was wondering if this kind of radiation that emit the black hole may impact the stability as well. I mean, maybe
Sure,
damping the
sure.
mode or something like
Sure.
that.
You know, if you leave the world of classical general relativity and you add, you know, quantization, the statement will be different. The black hole stability problem will be different. I am only interested, you know, as I said at the beginning with the disclaimer, just pure general relativity. We just want to see what does Einstein's theory predict before adding on anything else.
Okay.
And it's not clear how to add on these other things. I mean, it's not clear how to, I don't know. I don't think that the, you know, Hawking radiation is very is properly understood for mathematicians yet. So, for instance.
Okay, thanks.
Sure, thank you.
Thank you very much. Let me see. I don't see. There was another question, but I think you addressed that, which is like, yeah, I'm not sure if black holes in our universe are described by the Kerr solution, but what are the implications for them? I think you touched on that. So let's.
Well,
see.
I mean, black holes are not described by the Kerr spacetime in the sense that, you know, we expect that they are dynamical, right? And the black hole solution is stationary. So in that sense, it is true. But, you know, this is a bit like, it still might be a good model, basically. Even if, you know, these other effects, you can still think of them as lower order effects. Well, another reason why you would think that the Kerr black hole is not good is because when the Kerr solution is an empty, it's just the Kerr solution. There's nothing else. There's you don't have nothing around it. You know, in the universe, you have things around black holes, you have stars, but it still might be a good model for the local geometry near a black hole, near black hole.
Thank you. I think, okay, we have another question on YouTube. I think this will be our last one. So they're asking, this might be out of topic, but have you considered how the presence of charge in the black hole would affect stability?
So this is something that I mentioned very briefly in this shoulders of giants part. So this is something which one of our colleagues here at Princeton, Elena Georgi, is working on, and it well, it does affect the stability problem in the sense that, you know, mathematically it makes it much harder, because so if you consider, so there's a generalization of Kerr which has charge, which is Kerr-Newman black holes, and Kerr-Newman black holes, just their generalization with charge. And if you look at their stability, when you do linearized stability, you need to consider at the same time gravitational and electromagnetic perturbations, and they couple together, which means that then you cannot have, you know, I showed you at the beginning that you have this nice Teukolsky master equation, which describes the electromagnetic perturbations, and it describes the gravitational perturbations, but, you know, it describes them decoupled. This is for Kerr. If you look at Kerr-Newman, they will be coupled. So there's not a single Teukolsky equation. So things will be much harder. And from what I understand, from listening to her talks, that will probably be especially relevant in the case where you have large rotation. So if I understand correctly, some of other colleagues here at Princeton have done some simulations where they show that if you have sort of, so there's this idea in the physics literature, I think, that charge should not matter too much, and they kind of wanted to investigate this claim that charge doesn't matter. And I think they put a charge scalar field or something around the Kerr or Kerr-Newman black hole. And if you have spherical symmetry, so, you know, if you're Schwarzschild or Reiser-Nordström or whatever it is, then that maybe it's the Reiser-Nordström charge. Well, it dissipates. The charge dissipates very quickly. But when you have rotation, the charge stays on for much longer. So this will probably be more impactful in the more rotating case, in the rotate really where the black hole is rotating. And yeah, it does impact things, and it's not clear at all how it will impact. It's still, we have to wait for Elena to show us.
Cool. I think there was another question in this Slack in a communication, but so I'm gonna rephrase it because I don't forget exactly what was. But then the question is there a way to know the numbers of symmetries and those masses? And if you could please comment why you call them masses.
Okay, sure. So I can comment on why I call them masses,
Well,
and then I have to repeat. So I call them masses because in supersymmetric quantum chromodynamics, in this, so I said that this theorem was conjectured before by Aminov, Grassi, and Hatsuda, and it's something very clever, and it's based on the same kind of ideas that we then did the Kerr-de Sitter case. And their idea was, there's this paper about supersymmetric quantum chromodynamics. I know nothing about this, so my explanation will be very very basic. But from what I understand, there's something called Seiberg-Witten theory, and they look at hypermultiplets in this theory. I can't tell you exactly what that means now, but the point is they have masses, okay? This is, and they have, if you look at 3 hypermultiplets, they have masses M1, M2, and M3, okay? And that's why I call them masses. And actually their idea for putting out this conjecture is based on two things. So one thing is that it turns out in the quantum chromodynamics world, in the Seiberg-Witten theory, exchanging the masses, this is invariant. The theory is invariant. The predictions will be invariant. And so by analogy with that, Aminov, Grassi, and Hatsuda, this is my interpretation, they conjectured that you should also have invariance here. And then they did some numerics, which showed that they seem to have, the equations seem to have the same quasi-normal modes when you change the masses versus when it didn't, right? Okay, so what was the other question?
How many symmetries or masses, like, do you know? Because here, I think you show 3, and then in the other one, for the ADS one was 4. Is there a way like you can tell how many to expect or find?
I don't know exactly, but I can tell you this, which is there's some reason to think that here it should be 3 and in the other it should be 4, and it's related to how many singularities there are in the ODE. So so in ODE theory, so you have the Teukolsky ODE, right? And there's books from the 90s and earlier about ODE theory, which tells you that there can be singularities in your ODE, and there's a characterization of those singularities. And for the ODE for Kerr, you have singularities where? Well, you have them at the event horizon, R equals R plus. You have them at the Cauchy horizon, so the 2 roots of that delta, and you have a singularity at infinity, okay? In Kerr-de Sitter, where do you have roots? Again, you have roots at the roots of delta, and you have where do you have singularities? You have singularities at the roots of delta, which now will be 4, and you have a singularity at infinity. But there's some work in the 98 by Suzuki and I forgot the other people, so the group of 3 Japanese co-authors who showed that somehow one of those singularities can be removed, so that you end up with just 4 singularities. So Kerr, you have 3 singularities, you have 3 masses, and then Kerr-de Sitter, you have 4 singularities, so you have 4 masses. Okay, that's kind of the idea, but really this is all by very hand wavy, this is by drawing an analogy with supersymmetric quantum chromodynamics that we come up with these masses and these definitions of masses. And yeah, I can't tell you exactly, it's just somehow you see from counting number of parameters that in Kerr-de Sitter, you will want to have 4 masses. From counting parameters in Kerr, you will see that you want 3. But it's a bit like this. It's counting degrees of freedom if you want.
Okay, thank you. I think we're way past the hour. Thank you very much for contributing to Law Physics, and for everyone, please stay tuned for our next webinars. Thank you very much.
Thank you so much.
Bye-bye.
Bye. I'm sorry to have taken so long.
No worries.
No worries.
Okay, I think
you haven't beaten a record. Our record has been of an hour and a half.